All right, good afternoon. So, we left off in the last lecture on lossless compression techniques, right? And after this, we'll go to lossy techniques, which is what we use for multimedia, right? So we looked at Huffman coding, and we sort of mentioned the. So we left off with the dictionary-based coding techniques. So dictionary-based coding techniques, you want to create a dictionary of terms. It's the code words that you use for each sequence of symbols is the same size, right? Unless the Huffman coding where it's a bit-based entry. So the idea here is, from the input, you figure out a sequence of symbols and you replace them with one particular symbol, right? So if you see an input sequence of certain number of A's and B's, for example, you want to be able to send fewer symbols, right? So you have to create this dictionary on the sender side, and hopefully you can send it to the receiver side or what have you. You can think of doing this with the English text or what have you. But in the multimedia sense, you would like to build this on the fly. You would like to build this on the fly where you figure out about the input sequences, and then the receiving end, while it's decoding, also builds this dictionary that it uses for decoding, right? And this is used in the GIF compression mechanism. So we kind of left off with looking at the algorithm. The way the algorithm works is it looks at the current symbol and it looks at the previous symbol, and it tries to see if the previous symbol had a match in the dictionary that it's built as it progresses, and if there's a match, it tries to replace it with the previous entry, right? So in this particular stuff, S is the previous symbol and C is the current symbol. And both the sender and the receiver, both the compressor and the decompressor, have to start off with some state. So they start off with the notion that A is 1, B is 2, and C is 3, right? So that they have to both agree, and then they progress. So so if you're transmitting the symbol A, B, A, the first A, so the previous symbol would have been A. You start off with the next symbol as B, and you've never seen anything, or you've seen A, which is the previous string, as what you have in here. So you output 1, and the next time you see B, you output 2. But you're still, while you're doing this, you're building this sequence of things, right? You're building this dictionary, right? So you know that A and B, you saw it and you notice it, and you remember this stuff. So you're building this dictionary internally, and you have code words for that. So in the future, when you see A and B, you know that you've seen A, B in the past. So you have to look to see if that S happens to be in the strings that you've seen before, and if you have, then you replace that with that output, right? By doing this, you send less data than you have to. So in this case, the particular example, you send 9 characters instead of 14 characters. And the key here is the codes are still, if you're sending 8 bits, they're still 8 bits, right? So they're not variable length as whatever. So you're avoiding sending multiple sequences. So the longer this stuff goes, the more you learn, right? So for example, when you go towards here, you learn this A, B, B because you saw A, B, and you learn more sequence. So the longer you do this compression, the more you have likelihood of finding longer sequence, right? So the initial, you don't find longer sequence. Towards the end, you see longer sequence. But practical aspects is you have to keep track of this dictionary, right? And you'll have implementation details which restrict how much you can store, right? For example, if the symbol space is 256, 8-bit 256, right? Then you still have lots of sequence here, but it's kind of manageable. When if you're talking about a 24-bit number where you have 16 million different combinations, then your symbol table can be quite large, right? So in practical sense, you may have to either throw away you have to do some sort of least recently used or something to flush these things. So it's good if the object that you're trying to compress is big, but not too big, right? So if you're running it for gigabytes of files, then this table may get too large. You may have to flush this stuff, right? And the way the decoding works, So you essentially get the 1, 2, 4, 5, 2, 3, which is what is transmitted. You know that 1 corresponds to A, 2 corresponds to B, 3 corresponds to C, and you start off and you the first time you get a 1, it can only be A, so you replace that with A, right? And the next symbol you get is 2, and the 2 would have been a B. So you remember A and B has the tree, and A and B has a tree and tree has 4, right? So you're building this code tree and the string table as you move along. So if you follow through the algorithm, so essentially when you're decoding, you're building this tree on the fly. So the compression and decompression can happen without transmitting the string table, right? Because the string table evolves with time, but the decoder can do this on the fly, right? This is a class of string matching algorithms. So if you take a theory course, you'll probably find a lot more interesting algorithms than what we are seeing here. Again, the goal in all the systems is you want some algorithm which is suitable for multimedia, and you also want these things to be reasonably computable, right? So we don't want something very complex because you have to do this compression and decompression on the fly. So depending on the technology where we were, right? So GIF was pretty popular in the early 90s, right? So depending on the computers in that time, you have to worry about how long it takes to compress the image, decompress the image, so which may restrict what kind of algorithms are used. So there are probably far more better algorithms from a theory perspective, but practical implementation says that this is reasonable enough for what you're trying to do, right? And again, so in real world applications, you have to worry about how to manage this string table, so you don't want it to be too large. So in modern computers, you have enough memory to manage this stuff, but think of where you use these GIFs, right? You use it on your cell phone, say your cell phone or low-end devices like that. So you may not be able to build a large enough string table, right? So that's one of the concerns. And a more modern algorithm is the arithmetic coding algorithm. And so where it treats the whole, you can treat the whole image, whole data as a vector, and you're not restricted to treating them as 8-bit or whatever. You can treat multiple bits, right? And the description is in the book. I'm not going to go through that because it's not actively used in any of the modern media encoding algorithms, right? Though it's one of the things that you will see coming up in the future schemes, because as we move forward, technology makes it such that the newer encoders are capable of doing more computation. So you think of seeing arithmetic coding. Arithmetic coding is more efficient. It gives you more compression, but it's also more complex. So it's something that you would see in the future, right? So we are still looking at this. We are still in the lossless realm. So you can think of using what we know on what we know about images and stuff to do lossless compression. So one of the key observations which we kind of mentioned it before is most of the physical objects that you tend to look at has a lot of redundancy. There's shades of color. You don't usually see abrupt changes. There's slow changes in color. So if you look at the differences between the previous and the current scheme and stuff, there's not much change, right? So if you plot the histogram of the original image, so this is the histogram of this particular grayscale image. So essentially, this shows that the x-axis shows the different color values, grayscale 8-bit, right? So you have 0 to 255 value, and y-axis shows how popular each particular color is, right? So for most of the compression schemes, you want to reduce the dynamic range, because the more range you have, the more symbols you have. The more symbols you have, the more complex it is to compress them and all those things. You're trying to find simpletons or something. So if you can somehow, the goal of all these compression techniques is to somehow make it from here to something like this, where there are fewer symbols, right? The idea here is, suppose you want to transmit 1, 2, 3, 4, 5, right? There are 5 different symbols which would be sort of like what you see on the left. You have more symbols, you have more possible combinations, right? And suppose I can do something such that I only get 1, 3, and 5, right? Or let's suppose I have 1 and 3, right? That means there's more combinations of 1, more combinations of 3, and so it's likely that if you were to transmit something like 1, 2, 5, 3, 1, right? And let's say in the new scheme you only have 1 and 2, right? In a simple way where anything from here, this range becomes this, and this range becomes this, right? So this particular string that you had would be transformed to something like 1, right? So if you were to do this, then you have more redundancy that you can incorporate, right? So when you're going to talk about lossy techniques, you're going to do some things much more drastic than what we can do here. But even in the case of image, if you can do a diff within the image, you still get something where some of the components are more popular, right? The reason is the difference between any two values is small, not large, right? So if you're only showing the differences, the small values tend to be dominating, right? So rather than sending a lot of different values, you send the smaller ones, right? Does that make sense? So one of the popular coders that use this stuff is the lossless JPEG. So JPEG has 4 different modes, right? And we'll see what the other 3 modes later on. You probably never heard of or never seen lossless JPEG because it's there for completion's sake, right? The standard defines lossless JPEG. Very few people use lossless JPEG because you get horrendous compression ratios, right? So if you want to take a picture of something, you don't want to do lossless JPEG because you maybe get like one time or half the original size. You may think of using this for medical images and stuff. So it's not really used, but it's a good way to kind of get into the real JPEG, right? So the idea here, so this lossless JPEG works completely different than the lossy JPEG that we're all used to, right? In fact, many of the systems may not know how to deal with this particular JPEG because it's completely different. So you need to have different set of codes different C code to manipulate both these images. The idea here is it's a predictive one like what we talked about in audio form, right? So if we want to predict some values and then we only encode the difference from the predicted value, right? So somehow we want to, instead of sending the values for here, we want to predict what this value should be, and we send the difference between what was predicted and what actually happened, right? So if the intuition was you can predict something fairly good, then you will be fairly off only by a little bit, right? If your prediction is bad, then you'll be off by a lot. Then you would be worse off. But if I can do a fairly good prediction, then the difference between the prediction and what really happens would be small. That means that the number of different symbols would be small, and the histogram would be the one we saw, right? Would be what you want, right? We're reducing the number of symbols. So there are what they do is they basically take a 2x2 matrix, right? And they name it like A, B, C, and they predict this X value, right? And they define 7 predictors. Some of them are fairly trivial, right? So the predictor number 1 says that this will be A. So predicted value is, so the whatever value you have here, this would be A. And then you find the difference between what was actually there and what you predict, right? The predictor is simple. So you only transmit the stuff. So if the image happens to be value 100, 100, 100, your prediction would be accurate because you predict that this will be 100, you predict this will be 100, and so on, and you win, right? And for obvious reasons, you have, so there are different predictors. So for example, if this happens to be the first column, you cannot use predictor 1, right? Because predictor 1 says something on the left. So if this is the first column, you cannot use predictor 1 because there's nothing on the left. So you have to use B, right? Predictor 2 for the first column, and for the first row, you have to do predictor. Yeah, the first bit you have to do. So there's some sort of restrictions on what predictor you can use because at the ends you don't have enough values. But otherwise, you have these different predictor values, and you find you transmit the difference, right? And then you encode whatever the new values using Huffman. So essentially, you take the difference, and then you do the Huffman coding that we talked about before. You have far fewer symbols, so you expect some sort of compression, right? So the book tells you some of the ratios that you can get for different images. So on the title like Lena football, F18 flowers and all are standard images that people use to analyze these things. So for the different images, you get certain amount of compression ratios, and you notice that for some cases the image actually gets bigger, right? Because one of the things you notice on the compression, you can actually get bigger under certain circumstances. But for the images, you get around 1:2 ratio, right? Which is not good at all, right? But it's what it is, right? So if you have like a 1 megapixel camera, right? 1 megapixel camera would have, if you think of them as color, you can think of them as 3 megabytes, right? 1 megapixel, and each pixel is 3 bytes, 24-bit, right? So you're going to have 3 megabytes, right? So if I do this compression like this, essentially you're saying a 3 megabytes image would be like 1 megabyte or 1.5 megabyte is the output compressed image, right? And that's usually not good enough because that's a fairly big number. If you use JPEG, you usually get around 100K or so. So this is fairly big, but it's lossless, right? Does that make sense? So if you think of like a 10 megapixel camera or something, if you do something like this, you get to be really bad, right? And even you're able to get some of the stuff like in the lossless JPEG, you're able to get those because you still. This only works because it's an image of a photograph, right? If you use this as an image of something else, if you use it as a random data, then this won't work because your predictor won't work, right? If you have random numbers, essentially you cannot predict the random number. Any number is equally likely, so your random prediction would always be off. So the difference image would still look more like this, whereas in a picture it's not the case, right? There's something that the book does not talk about, which is the notion of how to code the stuff, right? So you may wonder why I don't ask any of you to actually code one of the stuff, code say a JPEG encoder or LGW or one of those stuff, right? The reason is it's horrendously complicated to write this code because a lot of the things that we kind of mention here in the board turns out to be really yucky C code, right? Really yucky C code, which is definitely not portable. And if you, the reality is, in fact, like something like JPEG, right? There was one JPEG which came out of the JPEG Foundation, a sample library that they wrote. And it's very popular. It's used in most places that you see, right? You may use Mozilla, you may use IE or Safari or what have you. They all tend to use one library because somebody wrote this library. It's been debugged. It sort of works, and you don't want to mess with that, right? Because, and I'll show you why you don't want to mess with that. So in the Huffman coding, which is what you use in JPEG, I think in the example of the hello world, hello, we said something like this, right? And this was for H, and this is for E. This is for, so this is for E. This is for L. This is for L. This is for O, right? If you remember from the last lecture, right? So these are variable length coded stuff. So these are binary, right? So in the binary, when I say it in the board, it looks all fine. But real computers deal with characters, right? So if you go back to your C programming class or your architecture class or what have you, right? Most computers deal with groups of bits, right? They deal with bits, I mean characters, or most likely they deal with integers, right? And integers happen to be, depending on a particular architecture, 32-bit or 64-bit, right? What that means is, I'm going to talk about it in characters because it's sort of easy to say rather than 64-bit, which is pretty long. So if you use that in characters, right? So you're going to see this will come in as a char data structure, right? So your decoder has to get the first bit, right? When I say that in the board, I can say go to the next bit, right? How many of you used bit coding using bits? So which language did you use?
Well, I just kind of filled it out with some bit manipulation.
Okay. So is that how you used to? Yeah. So many of you may not have used bit fields because they're kind of really annoying to use. So one nice way to use them within C, you probably can't use that in your Java and all those things, is to use this structure, right? How many of you seen or manipulated those kind of structures? The few of you, right? So essentially, this tells you I'm creating a union of this character into these bit fields. Each, with the colon one means that I allocate one bit. So I sort of do this stuff, right? So many of you, I'm assuming, know C, right? So if I say the CHR equals 0x B1, right? So this would be B and this would be 1, right, in hexadecimal. If I do this, right, what would happen if I do, what is bit dot 1? It's sort of a trick question because the answer is, I don't know. Do you know why the answer is I don't know? You might have seen this in networking class, right? Remember, you must have done this H2 NS N2. For folks who've done the networking class, right? You might have done some functions like this, right? For folks who have taken architecture, you may have heard of this one, right? Big Indian, Little Indian, right? That comes over to hurt you here, right? Big Indian tells you what order these things are stored, right? So when I assign it like this, right? When I read the CHR, it'll come back as B1 on any architecture. But how it's assigned by, if you look in the bit field, depends on the particular architecture, right? So if you do it on the Spark machine, you would get 1. If you do it on the Intel machine, it's actually worse than that. You'll actually see this as the part of the 1, right? But the Intel machines actually store it as 1, 0, 0, 0, right? So bit.1 on these two popular architecture, like in the Spark machine, it'll be 1 because of this. On the Intel architecture, it'll be 1 because of this, right? If you don't trust me, you can try this on the thing, right? So this is horrendously non-portable, right? So if you write this code, you have to basically write a code for every architecture you can think of because the architecture changes, right? So assume that somehow you wrote this code which will give you the next bit, right? How would you work, right? So you have to find out the first bit, then the second bit, right? If you do it naively, you're going to have to do lots of this bit operation, whether you choose to or not, whether you do it or the compiler does it for you. When you use something like dot 1 and dot 2, internally the compiler has to do this thing because the underlying architecture may not provide any kind of bit operators, right? So it will have to do something sort of this nature, right? It will have to mask out. For example, to get the first bit, I would have to mask it with this 80, which will give me the last bit. Then I may have to write 7 bits to get the value or something, right? So if you do any kind of bit operations, this is sort of what you have to do to get this first bit, right? And in the case of getting the next bit, right? Next bit means that you need to know where you were. You need to figure out how to get this 1 bit, right? And so on and so forth. And imagine here, right? You only have 1 bit from, so when you say next bit, you have to go to the next character, right? Because this particular code is half in this character, half in the next character, and so on and so forth, right? So variable length code is nice because it's very compact. but it's horrendously hard to compute. In one of the things that you pointed out last week, if you lose synchronization, if you lose track of where you were, right, this whole thing kind of falls apart, right? So you have to know where you were, and you have to do all this kind of stuff to figure out where these boundaries are. You have to go beyond those things. So all the things that we talk about elegantly, saying, the code for O is 111. You're not going to see a 111. You're not going to match whatever the code with what you have. So even though you get good compression and all those things, LCW does not have this fate because LCW deals with them as characters. So you don't run into this problem. You don't get the same kind of compression, but you don't run into this problem. So anything like a JPEG encoder or decoder is really hard to read, right? In fact, I don't think anyone knows sort of why it works. It's been working since 92. We're happy to use the same library over and over again. But I'm sure like Adobe rewrote something for themselves internally, but it's one of those things where you don't want to touch it unless you really have to, right? And the reason is why is the BLC code. The book does not mention it because it kind of talks about like it's a good thing, but you have to realize that many of these operations are annoying, right? We can do this in a very inefficient fashion, doing all kind of bit operators and stuff. But if you do that, your whole the video and all those encoding operations are already fairly compute intensive, which you will see from your project one or other projects. So if you make a code not efficient and by doing lots more operations than you have to, then the whole thing is really awful. So you'll see that people do lots of other tricks to make it to do stuff that only they know what they're doing because there's a lot of bit operations and stuff, right? So if you, I believe, like I'm not sure what the IE8 is, but if you look at the credits for IE Explorer, they still credit the JPEG library code because you don't want to touch, you don't want to mess with those things, right? Does it make sense? So next, I'm going to go to the lossless compression, the chapter 8, right? So now it's getting more interesting because this is where we want to be, and I'm just going to go through this chapter a little bit because we don't want to go fully into the compression because that's not our goal. So I'm going to give a little bit overview of what the different techniques are and then explain them using how it's done in JPEG and stuff rather than going into the how why DCT works the way it does and all those things, which is beyond the scope of what you're trying to do. We just want to see how how these things work enough so we can understand what to expect, right? Yeah.
I think you have a typo with your slides. Chapter 8 is lossy compression, not lossless.
Oh, okay. Yeah, sorry. It's lossy. Yeah. Yeah, it's lossy. Yeah. Sorry. So in the lossy compression, the thing to remember is you're going to lose information permanently, right? So you're never going to get back. So there are different metrics, like I think I mentioned it before, in terms of how to figure out how good you're doing, right? You're not going to be able to find the table that we had before in terms of saying how good a compression is, the compression ratio and all those things, because compression ratio depends really on how much you want to lose, right? In the previous case, I can say LGW algorithm would give you compression ratio of 2. Here, the compression ratio can be, I can compress away everything into 1 bit, right? And I can compress away the whole image, right? So if you want the image to have no quality, then I can compress it away to 0, right? So you have to kind of balance both those two, right? So if you go all the way out, no images actually means that quality of 0. So you want something which is reasonable, and what is reasonable depends on what your particular stuff is. So usually you get about 10 to 20 for a reasonable compression, but that depends on what you're trying to do, right? But you still want some kind of metric, so you have things like mean square error and signal to noise ratio, peak signal to noise ratio, and stuff like that. I don't particularly think that these metrics are really all that useful because they go against what we've been saying all along. We've been saying that there's a lot of stuff that you cannot see, so we're going to drop them, and now we're going to turn around and say, I'm going to see how far you are from the stuff that you couldn't see, right? So anyway, so they go through multiple different steps. The primary way they lose information is through the quantization step, right? So generally what they do is they transform whatever object you have into some space where your physiological studies show that that particular space is easy to compress, right? So I do initial conversion. So in the case of the audio, we changed it from from the regular domain to the the mu-lar domain, the R space. So once we do the R space, then we can do the manipulation in that space. So we can do the quantization in that space because that space is supposed. So we know something about that space, right? So in the case of the JPEG and stuff, as you'll see, we change it from a spatial domain to a frequency domain, and then we can apply our notion of what we can drop. So we do the conversion first, then we do the quantization in that domain, which will give us, which will let us drop parameters that we can't see. And then we do our usual Huffman or whatever, right? So we reduce number of symbols, which is essentially what we are trying to do, and we give it to our entropy coding classes compression that we can think of, right? Again, there's a number of different ways of doing this quantization, and I think we saw one of the linear uniform quantization would be that you kind of quantize it in a equally, right? You take so if your values go from 0 to 1 million, you may say I'm only going to look at 10,000 to 100,000 or something. So you drop off all the other ones, and then between them you kind of sample equally. So you can say rather than having every value, I'm only going to look at every hundredth of value, and I'm going to store it, right? And there are two different values depending on how many numbers you get, odd or even. So you get the mid-rise and mid-rate, which is not that important. Essentially, you're doing the uniform stuff. Non-uniform stuff is you can, if you know something about the kind of objects that you're operating on, then you can transform into these spaces. So, example was the audio form, right? So we knew that the here is only it's doing it based on the ratios. So you can move it to this ratio space, R space, or what have you. And vector quantization is another way where if I can have a preconceived notion of what we are going to talk about, then I can take a whole bunch of quantization symbols and then quantize it into a simple event, right? Which is not used that much in the kind of multimedia we're talking about. So again, the motivation in all this thing is you want to transform from one space to some space which is easy for us to operate on, right? This is not lossy. There may be loss because of integer calculations and round off errors, but the goal here is not that this is lossy. Essentially, converting it to a domain where it's useful. And so then we can zero out most of the components, and we want to make sure that we zero out the right way. And the one that is used in JPEG is the discrete cosine transform, which is a DCT, and we'll look a little bit in detail into that. Not the way that the book goes through, because it goes way more detail, but I'm just going to give a high level gist of what happens, right? So the idea here is we take a small chunk of image, in this case it's actually 8 by 8, right? We take a 8 by 8 space in the spatial domain. Spatial domain is the domain that we usually associate as x and y, length and width kind of stuff. Then we convert them into the frequency domain, right? The idea of frequency domain is we split that image into a number of components. You add all of them together to get the original, right? So the first component is a DC component. DC component, you can think of them from the frequency domain. In the spatial domain, you can think of them as the average color of this block, right? So if you have an image like this, and if you have like values for all the stuff, right? If you find the average color for this whole thing, that's the DC component, right? So that if you only have that component, it says what's the average color, right? The first order frequency basically says there are two components of it, whether the change happens this way or this way, right? Actually, the book had you can think of this as something like this, right? So the idea here is the DC component is the one on the top, which gives you the average color, right? In this case, it's shown as a white. So the second one on the right and the bottom is the next level frequency stuff, right? Which shows you actually in this case whether the color change happens this way or this way, right? Vertical vertical or horizontal, right? Does that make sense? I'm talking about like this one or this one, right? And the other one have different combinations of those, right? And this one, the change happens throughout this change on all the pixels of the image, right? So this is called the high frequency, but essentially in the spatial domain, if there is a color change in every one of these pixels, right, that will be captured by this component, right? So you do a summation of all these frequency components. That's the way you. So when you do the transformation into the spatial domain, essentially you take the 8x8 matrix, you create another 8x8 matrix, right, where each coefficient tells you how much of that particular frequency should be in the output. So if you add all of them, you would get the original that you had, right? So in the original, if it had a S, right, in the transform domain, you will have enough of these components. If you add all of those, it will approximate this curve, right? Because there is some frequency component which tells you the color change at certain. So yeah, this would let's say be represented, let's say, by this one, right? So the coefficient of this particular block would tell you how prominent this particular stuff is, right? That's the intuition behind how this happens. The math behind it is in the book, which is not really where we don't need to understand all the math behind it. But the intuition is you want to convert them into this in this fashion, because what happens is we'll see the three different stuff. We mentioned it before too, that humans are not able to distinguish small changes, which means that it's very hard for us to see something over here. We will notice something on the DC component, right? So if you take an image which is red and change it into blue, we'll notice, right? So in terms of if you have a sky and one little square block of the sky change from blue to orange, you will notice. But something of this detail you won't notice. So when you do this transformation from your spatial domain to this frequency domain, right, where it still looks like 8x8, but essentially you are creating a long equation which says that this is represented by this frequency equation, right, where each of them is a cosine. There's a DC component and everything else is a cosine function, right? And you draw this long stuff, then we can drop the stuff based on what we know, right? And the reason why we picked DCT is it's easy to calculate. It's all the operations are in integer domain, which is important for practical purposes. We don't want to do floating point because most of the machines are not good for floating point. So all the transformations are in integer domain, right? So the spatial frequency essentially shows how many pixels change in that particular image block. The different coefficients tell you different frequency components that are part of the original stuff. So essentially, you convert it from the original component, original image into the DC component, into the frequency component, and then the inverse of this will get you back to the image that you originally had, right? So going back to JPEG, we did mention this before. So you take a raw image, right, and we convert them. So now I'm going to chapter 9 because the chapter 8 goes into a lot more detail about how the DCT works, right? If you're mathematically inclined, you may want to read through the stuff, but you can take it as face value that it actually captures what you're trying to do, and then move on from there, right? It also talks about wavelet coding, which is a newer form of coding. So instead of JPEG, the JPEG 2000 is a new standard which uses wavelets, which people who work in that field who believe in wavelets believe that it's the best things in sliced bread kind of stuff. In practice, wavelet coding tends to produce not that much different from what you have from DCT-based coding. The reason why the people are going from JPEG to JPEG 2000 was another thing was copyrights. One of the annoying things with all the multimedia stuff is there's somebody who's holding copyright for all the standards, and they want to, so they basically want to get paid for the copyrights, right? And intellectual property stuff is annoying here. So for example, for the GIF format, Unisys Corporation, which many of you may not have heard, they used to be a big computer company back in the 60s and 70s. They have a patent for GIF, right? Which means that they can ask money for every place they use GIF. And since web took off, that means they can make lots of money from all these companies. And so there's a move towards formats which have less copyright protection. But it's never took off because companies have copyrights on the most fundamental stuff, so it didn't quite catch up, right? So JPEG 2000 was supposed to be clean, but it didn't get good compression. And the people who hold the copyrights for JPEG haven't been going after people to get money, right? So we're kind of good for now, right? So essentially, you take in the JPEG standard, this is the vanilla JPEG standard. You take the image and convert it to the DCT form. So if you have a x by y matrix, it converts to UV, which is for practical purposes is the same size, right? You can make it larger, then you have more detail, right? So if you go in the previous stuff, there's nothing which prevents you from having it at 8 by 8, right? The input can be 8 by 8. The output can be 64 by 64. What that means is the output can have more higher frequencies than what you deal with. But since our goal is we're going to zero this out anyway, since we're going to get rid of this anyway, there's no point in making it have even higher resolution than this, right? So we choose. So we take a x, let's say 8 by 8 image, and we convert it into 8 by 8 image, right? Theoretically, you could convert it, like for example, 16 by 16, but it makes no sense because you're adding more frequency components, which you're going to get rid of anyway, so we don't have to bother with those, right? So you do this conversion, and again, and to reiterate, the reason why we are able to use JPEG, we are able to do anything with JPEG is you make these three observations, right? One is images change relatively little within that 8 by 8 block, right? The 8 by 8 is no magic, right? Can you think of a reason why you would choose 8 by 8 rather than 16 by 16 or 64 by 64? So you take this whole image and you convert them into this 8 by 8 blocks, right? So if you take an image, JPEG is essentially treating them as 8 by 8 blocks, right? So it's not, so even though we say it's a photograph, even though we say that things don't change all that much, each compression only looks at this little 8 by 8 section, right? And they're independent of each other. So if you compress something for this 8 by 8 block, the next 8 by 8 block is a completely independent process. And so what you will see is what you call blocking, right? So this is one of the aspects of JPEG which you may have noticed. So this is a graph I got from Wikipedia, but essentially what they do is they take an image, right, and they compress it with increasingly lower quality as you go from left to right, right? So the original image is this flower. So if you go from here to here, right, unfortunately again the display is not good enough for you to notice any difference here. So this is 100% quality, and let's say this is 80, 75. Usually you can't say anything wrong here. And when you get to here, it gets really bad, right? What really happens is when you have such a low, so it'll become black and white here because all the color components are lost, so you become black and white. But if you are somewhere here, you may notice what I said. So what happens is you're losing so many of the frequency components that you end up with the DC component, right? Remember the top left corner. The DC component is the average of the block, right? So you would notice that, like for example, this is pink, right? It's more likely like this, like a slight variation, but you only see the average color on the block. And you also notice that these are all square blocks, right? That's because you're compressing on 8 by 8 boundary. And if you have a large image, you don't notice it, but in a small image, you may notice it because it's treating each one of them separately. It's not treating, so the image is broken up into 8 by 8, right? So why would you choose something? Is there a reason why you would want to choose something which is larger rather than 8 by 8? Like let's say 64 by 64, right? What's the reason why you would want to use something larger, and what's the reason why you would want to use something which is smaller?
Well, I guess it might be nice to use something larger because then you get kind of a better picture of what's going on. You're not as isolated to just a small area. But I guess on the downside then, if you crank up the compression really high, then you get like, these really huge blocks of color instead of like, that's sort of still semi-recognizable as opposed to just having a big blob.
Yeah, but practically nobody, you should never compress it at this range, right? If you go to this low quality, there's not a whole lot you can do, right? Yeah. Yeah, so there's a compromise, right? I mean, you want to see how larger blocks means that you have more redundancy, you get more more quality, more information, you can do better stuff. But it also means that you need to have more memory and all those things. So 8x8 was a good compromise back then, and it may be different now, but that's part of the standard, right? Right. So the idea here is things change rather slowly. So so if you take 8x8 block, you expect this things to be not much to change, right? And the next one is we know that the studies show that people cannot see high spatial frequency, right? Which we call it as detail. People cannot see high frequency because in real life you don't have much high frequency component, right? You may have high frequency components which are added by your brain, but you don't actually see them, right? So for example, if I look at people here, right? For example, it's something like a hair, right? Your hair has lots of high frequency components because the color changes with every stuff. But most of the time, I don't actually, when human beings look around, they don't actually see every hair. I mean, they basically see you see a black hair, and then your brain fills it in with how the hair should look like. So you don't actually see what the hair is, but in general what human hair looks like. So it does the averaging, it knows what the color is, and then it kind of adds the detail, right? So even though it looks like we're seeing detail, we don't actually see it, so that's what we're using here. On the other aspect is we know that we can see color better than, we can see brightness better than color, right? So we use all these three components, right? So we first split the image into three color components which can use this observation, right? So we don't know anything about RGB, so we convert them into YCB, CR, or YUV, or one of those spaces where the brightness is one component and the other color chroma components are smaller. And then we can do this subsampling which we saw before, which essentially keeps 4 times as much of the brightness as the color one, right? So we use this. So we take the image, split them into 3 images. We can do this to operate on them differently, and we know that the spatial frequency is certain thing. So the DCT is designed so that we can use the second observation. Right? So that's why it converts from spatial to the frequency domain. Right. So essentially, the coder works like this. Right? So it takes an image, converts them from whatever space you have into something like YUV or something which can use the observation 3. And then it does the scaling, make the color image smaller than the black and white image. You send it to DCT, right? DCT, again, is not a lossy compression. DCT's goal is to let you use the observation 2, that we can't see the high frequency component. Then we do quantization, which essentially drops the components in this context, using a quantization table, which we'll see what that is. Then we get the output, and we'll do a zigzag format. Again, this helps in the Huffman coding. And then we do 2 different kinds of coding based on the 2 components. We do different coding for the DC component and one for the AC component. And again, the reason being, DC component is the average color of the particular block. And that tends to change a lot, because if you take 8x8 block and if you look at the average color, right? So even though an image may be roughly shaded in a smooth fashion, if you hit an 8x8 block, the color changes would be abrupt, right? So if you use it as use the regular run length coding techniques, this abrupt changes wouldn't give you good compression. So essentially, you take the DC component and then you do a differencing on those, right? the idea here is you may have a hue where, let's say, you're changing from red, dark red to light red. The average values across these different blocks would change, but the difference is still small enough that you can get good compression using DCM. And then you can run your usual run-length coding, like Huffman coding on this stuff. And then so essentially you send them, you compress those and then send them across, right? And so if you use 8x8 block, and that's one of the reasons, why you begin to see the square aspect of it, right? And the wavelet coding would not see the new coding would not see the square one because it's a wavelet function, so you get curves, but it has other issues, right? I'll stop with that and we'll continue on Monday.